Thanks, Joe. For that, and especially also thanks to PetroLearn for including me on their monthly series. I do some quite a bit of consulting with PetroLearn on the synthetic geothermal reservoir and other projects like oil and gas conversion. But this one is about using a geothermal heat pump approach, a new approach for focused really on grid cost and grid energy storage. And that's going to help us decarbonize both the building and the grid, and as well as lower the cost of energy for both. Okay, so well, that pinging is a little bit distracting, sorry. The grid cost and CO2 management is, we're going to do this with a simple proven technique. So air source heat pump, so that's like your air conditioner on the side of your house. The water source heat pump is very similar, both commercially available equipment, and then the borehole thermal energy storage system. And so these things together are what I'm calling GABES. And we'll get into what that definition is. Now, the reason that this is exciting to me is the cost and the CO2, but I think it's especially good because it's a really huge investment opportunity. In the US alone, there's 540 million buildings. So there is a huge amount of investment opportunity. These ideas are all open source. And so, there's intentionally no patents. Where we really want to encourage people to go out and use this technology, these ideas, and adapt it to their particular applications. All right, so let's do a big picture. And this is generally attributed to Einstein, but the words that we're going to read are, we can't solve our problems using the same thinking that we use to create them. And we definitely have a problem. And that problem is rising atmospheric CO2 and the consequences that is going to cause. And so the thinking that created the problem included that energy is cheap, so efficiency doesn't matter, and fossil fuel is our stored energy source to smooth out peaks and valleys. And so we're going to have to choose what's the future that we give our grandchildren as a result of that rising CO2. What level of warming are we going to control to? And GABES isn't the whole solution, but it is one of the solutions that could help with global climate change. So it's going to decarbonize in all climates, both the electrical grid and building heating and cooling. It's going to lower the cost of power. So this is a nice change from the current path that we're on. We're going to be able to store huge amounts of excess grid power, and that's actually going to enable more and faster low greenhouse gas power to come online, whether that's intermittent, like wind and solar, or baseload, like nuclear and geothermal. It also creates unprecedented job creation because we have to go to every building and we have to drill holes for every building. And jobs and lower energy costs are really part of the key of the ideas around environmental and social justice. And again, we're not going to do any of those things unless there's profitable investment and areas. All right, so what is GABES? All right, it's an engineer's acronym for Grid Amplified Building Energy Seasonal Storage. And so we're going to break down those phrases and see what that's about. Grid amplified. Okay, so an air source heat pump takes 1 unit of electricity and delivers 4 or more units of heating or cooling. So that's amplifying the effect of grid power. Building energy, that's just building heating and cooling. So water source heat pumps, because they use water, are much more efficient than systems that use air. More efficient means fewer kilowatt hours per year. But from a grid perspective, even more important is less demand, kilowatts. How much power does it actually take to deliver heating and cooling on the hottest hour or the coldest hour of the year? And seasonal storage, this is the borehole thermal energy storage system. It's a series of drilled geothermal boreholes, and we'll see what that is in a minute. And we can store electric energy for building heating and cooling for anywhere from diurnally to seasonally, 1,000 hours or more. So let's take a look at what we're talking about to make sure we understand. A geothermal heat pump borehole is a drilled hole in the ground, and it has a loop of plastic pipe in it, and that loop is grouted into the ground. So it is not a well. There's no flow into or out of the ground formation. The only flow is through the plastic pipes, completely self-contained, and then it's conductive heat transfer out into the formation that the hole is drilled in, the plastic pipe is in. So in a traditional geothermal heat pump array, if we're in the cooling mode, we're pushing heat out through widely spaced boreholes in parallel flow. In a BTES, it's the opposite. We're using radial flow, and the boreholes are much closer together. And we're going to continue on with this key differences between these two ways to drill the same boreholes. All right, so physical comparison, we've already looked at parallel flow versus radial flow. So in a traditional geothermal heat pump array, where our goal is to conduct heat away from the boreholes and into the ground that is beyond the borehole array using conduction. So from the center of the field, that's quite a long ways. And you have to cross other boreholes to get rid of the heat. And so the center tends to heat up. As a result, it's not effective in extreme climates. There's just too much heat being transferred over too long a distance for too much of the year. These also have quite a large surface footprint in order to improve their heat transfer. So here we're not using the outside ground. We're using the air source heat pump, either a chiller or a heat pump to provide heat. This one's showing a chiller, which are inexpensive devices and can be operated when it is efficient to do so. As a result, it's effective in all climate, and it has a much smaller surface footprint, which is important for urban areas. Okay, so now let's look at the value comparison. So we have a lot of boreholes. That means large CapEx, and this is the dominant reason why geothermal heat pumps are not more widely used. There's a grid benefit when the HVAC runs because it reduces demand, but this is very seldom incorporated into the economics. The bigger it is, the worse it does. That's a surface area to volume ratio effect, and it's viewed as a building efficiency tool. So we're going to be looking at 40 to 50% reduction in CapEx in the boreholes. We're going to have that grid benefit when the HVAC runs, but we're also going to use the air source heat pump to add energy to the BTES, and this using electricity off peak is beneficial to the grid as well, and storing energy in the BTES. And so, interestingly, the bigger the better. Now, the bigger the volume to surface area ratio is, the better the energy storage system performs. It is still a building efficiency tool, but it's primarily a grid cost and CO2 tool. So I want to look at a couple of case studies where a BTES has been used, and then we'll look at, and that it's not where GABES is used, but we'll take a look at it and see what happens if GABES had been used instead. So the first one of the most famous, is a completely solar thermally heated community up near Calgary. Now, Calgary does have a pretty good solar resource, but of course it's quite seasonal as well. And so they're using the BTES to store solar thermal energy seasonally and diurnally in the winter to meet the heating loads, 95%. And it gets cold up there for sure. So the way it works is they've got solar thermal collectors on top of the buildings, and in the summer and warm winter days, they take that excess heat and they put it into the ground, into the BTES. Then when winter comes along, they pull that heat out and circulate hot water through the buildings, through the homes to heat them. And this I've drawn in a little cartoon here of what the BTES looks, of where the BTES is and how big it is about. So it's very small in relation to the number of buildings that it's serving. So this particular one is, about 120, 150 feet in diameter and about the same depth. So the GABES improvement would be to use an air source heat pump to store the heat in the summer and to add heat during the winter, and then geothermal heat pumps to recover it in the winter. So if GABES had been used at Drake's Landing, one, there would probably be a lot more of them. There would not be just a single demonstration project built in 2007. But the differences would be that the air source heat pump would be what is adding heat to the BTES, and then warm water instead of hot water would be pulled out and delivered to all the buildings where they would have their own individual water source heat pumps. This is an industrial unit, but and that heat pump in each building is what delivers the building heat to the homes. So case study at the Marine Corps Logistics Base in Albany, Georgia. This is much more similar to GABES, very similar in fact. So it's a cooling dominant environment. And again, they use the BTES. As you can see, this is the project where that graphic, this cartoon graphic of a BTES came from. And what they did is, instead of using an electric chiller, they used dry coolers. And so the way that works is the dry cooler operates when the air temperature is quite a bit cooler than the center of the BTES. And so then it turns on and extracts heat out of the ground, pushes the heat into the air, and returns cooled water back to the center. And then the building pulls cold water out of the center of the BTES, delivers it to the heat pump, the water source heat pump in the building, and that picks up the heat from the building and returns it to the outside. So that water then flows through plastic pipe to the center to cool off and make the cooling system more efficient. So if GABES had been used, so here's a picture of that again, and if GABES had been used at this project, the only difference would be that we would substitute that chiller. We would substitute an air-cooled chiller for that radiator system that they have. So one more case study, which is not does not use a BTES, but it does illustrate the value of district heating and cooling systems. And this is an ambient loop geothermal heat pump system at Colorado Mesa University. And it works really well. GABES can improve that performance even better. So let's see what that current performance is. It's a single loop ambient system. It's a lot of buildings, over 1 million square feet, which is over 100,000 square meters. It provides heating, cooling, hot water, and quite a large heating and cooling load. Now, by having this district energy system, what they've done is they've actually found that the size of the loop field, the number of boreholes that they need compared to single building geothermal heat pumps, is about half. And with GABES, we're going to be able to cut that number down even further and create additional grid benefit. So some of the benefits that they showed: HVAC system demand reduced a megawatt. That's a grid benefit. Water use was reduced. That's a benefit in our society all over the world. And they haven't had to by recycling heat in this district energy system, they haven't had to use their gas-fired boilers for 5 years. It may actually be 10 years. All right, so GABES can really improve geothermal heat pump projects. We can use an air source heat pump for heat transfer that reduces the cost of the boreholes. It improves peak hour performance and provides green energy storage. The lower capital cost makes it more financeable, more deployable. The B test is smaller and cheaper. Air source heat pumps are inexpensive and efficient. And finally, all of this makes it more valuable to a power company, which justifies financial incentive. So it's grid amplified building energy seasonal storage, 3 proven technologies, more valuable than traditional geothermal heat pump. And I keep saying grid management tool. So let's really delve into that in this next section. So the grid needs to change. This is part of not using the same thinking. So the old paradigm was fossil fuel, we have changing load, and we're going to burn fossil fuel to match whatever the changing load is. We don't provide heating from the grid as a general rule, and the energy storage system is the fossil fuel itself. The new paradigm is that we have variable generation from wind and solar, and so we actually need to adjust load to meet the generation that's happening, and we're going to do that with storage and dispatchable load. We have to supply heating from the grid if we're going to decarbonize, and so we're going to need new storage mechanisms. So the thinking that is now happening out there is that's creating problems is that we're ignoring end-use technology. And since wind and PV don't emit CO2, we're building a lot of it, which is creating a new set of problems. So let's take a look at those. This is California's famous, what's called the duck curve, because it sort of looks like a duck. And it is generally at March 31st is when they generally publish this. And what this is showing is that as they've added more and more and more solar to California, the power that has to be supplied by the other power assets on the grid drops way down in the middle of the day in the spring, especially. And this creates a number of problems. One is ramping power plants up and down, but this very steep ramp here at sunset means that we are basically having to fire natural gas to track this rapid increase in demand. And as you can see over time, the peak demand continues to go up for a number of reasons. But so GABES is going to help with this. So it's going to be able to store that excess solar power. It's going to grow the peak load. So these are the problems. These more solar over time is decreasing it. We're growing peak load. And that reason that peak is still growing is that we're still using inefficient air conditioners. So let's not do that. Cold water is more efficient than hot air. So with GABES, we're going to be able to cut that peak demand by the air conditioning demand by 50%. And we can store that excess solar and flatten out this bottom. And so those are both big grid benefits. But California's problem is with too much energy is going to get worse. In 2030, they're going to have 15,000 gigawatts that have to be curtailed in the middle of the day. 15,000. That's like almost 30 nuclear power plants. Not that they have nuclear power plants, but just to put it in scale, got to turn off 30 nuclear power plants every day. And 75 gigawatt hours, which is enough to charge every battery in the country right now. So, this is going to result in, these are large curtailments. And there's big price differentials on the grid. So here in the low periods of time, the cost of power can even be negative, very low. And during the heat of the summer, it can go very high. We're seeing numbers here over $200. So a $200 a megawatt hour differential. So if we can store cold in the spring and not generate power in the summer, that's a pretty big arbitrage difference. And that creates grid value. But California isn't the only one who's having this issue. Growing curtailments per year. It's happening in Texas. It's happening in the middle of the US. So let's take a look at the middle of the US. They're going to add, in the next 4 years, they're going to add almost 20 gigawatts more of solar and wind. So their curtailments are also going to grow. And it's a universal problem. In the Pacific Northwest, it's too much hydro and wind. Arizona and Hawaii, too much solar. The Southeast, nuclear and solar of the US. And the United Kingdom has too much wind. I've heard numbers as much as 25% of wind generation potential is curtailed every year. So geothermal heat pumps really help with the problems of electrifying the grid. This is a Rhode Island study comparing conventional geothermal heat pumps with conventional air source heat pumps, looking at 2050. So just to get oriented here, the dotted line is where Rhode Island is today. It's a population of only 1 million people. If they electrify everything else except transportation, load growth, et cetera, in 2050, they're going to have this light gray line. And this is where the peak demand occurs, this just a couple of hours a year. And so it's going to grow from 26 to 37. Well, if they electrify with air source heat pumps, which switch to electric resistance heating in the winter, they're going to go to 73,000. So basically, they're going to double the amount of generation that they require for 1 million people. That's a lot of megawatts of capacity. If they use conventional geothermal heat pumps, they're only going to increase 7 gigawatts. So that's, and again, it's a switch from winter to summer. The load factor is a measure of how expensive power is on the grid. And so this is, again, an illustration of how geothermal heat pumps help reduce power cost. But what if we use GABES? So if we use GABES, it's very likely that we can actually cut the winter peak to less than what they're projecting will be the peak if they don't do anything with electrifying heating. So it's likely that the load factor would go up to 70 to 80%, which lowers power cost. So, but that's not the approach that we're currently taking across the US. We've created our problems with high technology. And so the solution, we're going to use the same thinking, and we're thinking that high technology is again the solution. We're going to deploy batteries. So they're expensive. We're going to deploy a lot of them. This is a large underestimate by the US Energy Information Agency. It's going to probably be double or triple that in reality. And what are we going to use those batteries for in the middle of the summer? Well, we're going to still be using them to run inefficient air conditioners. So we've got a gigantic technology mismatch here. To me, this is like putting buggy wheels on a sports car. It makes no sense. Yeah, you can sort of go forward, get down the road if you have to, but this is not an integrated solution. So let's look at how GABES can make energy storage an integrated solution. So let's take a look at the large amount of excess wind power in Texas and the challenges that we're facing there. So very hot in the summer, peak temperatures of 110. So that's about 41 or 42 degrees Celsius. And so we've got very high summer demand, and we've got low spring demand. Why do we have low spring demand? Because it's cool. Okay, so let's look at the wind in the windy part of Texas. Well, we've got high spring wind and low summer wind, so we've got a seasonal mismatch. Now, when we're looking at wind graphs, don't forget that generation is proportional to wind speed cubed. So when we go from 10 to 20, we get 8 times more power. So this is a big increase in total generation over summer. But we also have a problem even in August that the wind is high in the morning when air temperatures are cool and we don't need power, and it drops off right at the heat of the day at sunset when solar is also dropping off. So we've got a diurnal mismatch as well. So now let's take a look at what GABES does for us. First, it's going to cut our peak demand by 50%. All water source heat pump, geothermal heat pumps do that. But now we've got a way to store that spring wind, and we're going to store it when air source heat pumps are operating in cool or cold air temperatures, which makes them very efficient. We can also use that wind in the morning and at night to store cool during the off-peak hours. And because we have addressed peak demand, that sag in wind at the end of the day is much less important. So this is an approach that works in all climate. Let's take a look at it. Saudi Arabia is actually one of the places where this idea first started of GABES. And so we really want to avoid running air-cooled air conditioners when it's 117 degrees outside. That creates huge peak demand. So instead, what we want to do is we want to store cool in the spring, and we want to take advantage of the fact that it's so much cooler at night. I mean, it's not cool, but from an electric use perspective, it's much cooler. And the advantage of running the air conditioning load at night is that we know it's going to be running. We know we're going to have demand in the day. We increase the demand at night, and that's what drives the conversion from simple cycle gas turbines to combined cycle gas turbines, and that results in both less fuel cost and 1/3 less carbon emissions. So even though it's still fossil fuel, it's much more. It's a big benefit. Okay, Duluth, Minnesota is a pretty cold place for a big city, and so they have a minimum temperature of about -30. C, which is about -22 F. So what we want to do is we want to store the fall warmth, and during the day it warms up to where air source heat pumps can add heat back into the ground, and that's what we want to do. So just to summarize here, so GABES can green up and reduce the cost of building heating, cooling, and manage grid loads. So instead of using simple cycle gas turbines and batteries, we can store energy in the ground and deliver it through heat pump-based district heating and cooling systems. It applies in Saudi Arabia with that conversion to combined cycle, and of course, providing a way to integrate solar as well. Washington State, Ethiopia, Norway, surplus hydro. Wind or nuclear, Texas, United Kingdom, France. Kenya actually has excess geothermal power, and Hawaii and California and other places around the world have excess PV. So we can really integrate into the grid anywhere in the world. And the great thing about geothermal heat pumps and geothermal boreholes is that we have dirt everywhere. We don't need an aquifer. We don't need any sort of specialized geology. We can put this literally anywhere on Earth. Okay, so I want to show you a couple of the little projects I'm working on. I want to emphasize that these are very preliminary. The start of a couple of studies. One is in a far northern community. It's a 100% fossil fuel community, diesel engines for power, fuel oil for heating. And these letters represent a series of groupings of large buildings in this town. So the idea that's been around for a long time is, well, hey, let's use the engine heat from the power plant to heat the buildings. So that means that we have to, that's instantaneous heat use. So that means that we can only hook up enough buildings to meet peak demand. And if that's the case, we can only hook up 10% of the buildings. But if we use GABES, if we store that engine heat, even when we don't instantaneously need it, we can do 100% of these buildings with the same engine heat source. So this is what it looks like. We've got an engine. We're going to take that heat. We're going to put the heat in the ground. We're then going to pull that heat out, use it in a district heat pump energy system. So the engine supplies both electricity and heat to the community. We can also still use an air source heat pump. This is going to burn more diesel, of course, to run the air source heat pump, but we get we can get 4 units of heat in for every unit of electricity, plus we get the engine heat. So this might not make sense, except that these houses are currently burning diesel to stay warm in the winter. So it does actually make sense thermodynamically to do it this way. But we can go farther than that. We could potentially add wind turbines. And the problem with a wind turbine on a microgrid is that it's very noisy power, and so it's hard to regulate. Well, we can use the air source heat pump and have it basically be a variable load to help smooth out the operation of the wind turbine. And batteries will be useful for that also, but batteries have a limited duration. So this is going to allow us to potentially go to all buildings in the town. We can use the air source heat pump to replace engine heat, especially with wind turbines. We have to. We can decarbonize both heating and cooling, heating and power. We can get an overall community CO2 reduction of perhaps is more than 80%. It looks like it would be profitable to do this. In other words, you could pay it off with the cost savings, and that makes it replicable to other communities. So let's take a look at some of the modeling that's being done on this project. So we've got our little GABES cartoon here. So we're only going to model in the finite element, we're only going to model 1/8 slice. And so as you can see, we've got a series of geothermal boreholes in the model. And this is a grid. You can see the boreholes where they are. Now, this is one of the innovations that we're testing, is to actually make the outside boreholes deeper than the inside boreholes. So the inside is hotter, so that heat is being conducted away from this, but it's also being picked up by the wells that are deeper and deeper. And so, it looks promising. So we're seeing here that we've got a temperature profile, and that you can see that it is, in fact, probably doing some of picking that up. We haven't analyzed it in enough detail for me to give you results yet. And it's a cold ground. It's actually permafrost. So we have to melt that, and it's going to take a couple of years to come to steady state temperature. So what about all that energy that's being used to warm up that? Well, an electrochemical battery also has a lot of energy that goes into it to make it functional. And so I think we've got to look at this in the big picture. This is a very localized impact, whereas precious metals and other things are a much more global impact. But the impacts always occur over the horizon from where we are. So, full build out, maybe we can get every building in the town eventually. I'm also working with the city of Vernal, Utah. We're in the conceptual phase. This would be integrated with the planned sewer and water system upgrades. That's the purple and yellow lines on the drawing. We've submitted a design grant application, and partners are welcome. The goal is replicable infrastructure investment, and this one. So it looks quite promising, and we can put a B test right in the middle of the town where a park is planned. The red boxes are buildings that are that have excess heat, and the blue boxes are buildings that need heat in the winter. So getting to deployment. So we need utility participation in the evaluation. We've got to capture the value of GABES at large deployment, not a single deployment, that doesn't affect the grid, but at multiple deployments, we need to capture what that value is to the grid and incentivize it. We continue to need to do building grid and B-test modeling, quantify the job and local economic benefit, and all of this will demonstrate the investment viability. So one of the challenges for utility is that we're creating value in a lot of different categories. So what they call supply side planning and operation. So that's the grid assets, which ones are going to now be needed versus otherwise, which ones can now retire, can we add more wind, how do we optimize our battery use, our energy storage. So this is a skill that's already going on and being learned in the utility of how best to use batteries. So GABES is just like that, except that now it has a seasonal component as well. Demand side planning, this is an efficiency measure. It's a peak reduction measure. It's a fuel switching measure. In other words, switching from natural gas to electricity. This causes investor-owned utilities a little bit of heartburn, I'll be honest with you. But there is a role for natural gas utilities in GABES as well. Transmission and distribution, well, if we don't need as much power in the cities, then we don't need to build as much transmission. So this is what's known in their lingo as a non-wires alternative. And rate making, because we're selling more power, that lowers the system cost. That shows up in rate making. So it's complicated, but if we tackle that, what we end up with is a couple of financial options. We can do utility can do rate-based investment for the B test for the piping infrastructure. They can do CapEx incentives, and as I said, both electric and natural gas utilities can participate. So, is a natural gas utility a natural gas utility? That seems like an obvious yes, but I would say the answer is no. A natural gas utility is an investment company that puts underground piping infrastructure in place and delivers building energy with it. Okay, that's exactly what GABES is, underground piping infrastructure that delivers energy to buildings. So what's interesting about GABES and all district energy geothermal heat pump systems is that they represent a really good way for natural gas utilities to transition from delivering fossil fuel to green energy, and to do so in exactly the same business model that they are already in. So just a different energy carrier is the only difference. So to get GABES deployed, we want to hit these goals: energy benefits, greenhouse gas reduction, CapEx reduction. And if we do that, we're going to improve financeability. So where are we on this? So we can reduce power consumption by 40%. We can eliminate natural gas, and we can do so without cooling water. So we do get those benefits. Those also lead to greenhouse gas reduction, 75% for heating, 60% for cooling. Well, why is it only 75% for heating? Well, because the electric grid still has carbon on it. So we've got to take account of that. We've 100% eliminated carbon at the building itself, but if we include the grid, it's not a 100% elimination. 40% fewer boreholes, utility incentives, and if we do a lot of it, we're going to get better at it, and if we get better at it, that lowers cost, and so that is economy of scale. It's a volume type economy of scale. All of those things then do make it financeable, and if it's financeable, large-scale, rapid deployment as possible, and we can start talking seriously about that $1 billion a year. But is 1 billion really, what can this support? Well, here is a study of conventional geothermal heat pumps applied across the US, and these are the benefits that were generated, my estimates of what the cost savings and peak reductions are. Happy to share that with you if you want to know in more detail, but what's the present value of that? $1 trillion. Okay, well, it takes 1,000 years at $1 billion a year to do $1 trillion. So yes, we can easily do $1 billion a year on the benefits that are created from geothermal heat pumps. So I want to talk about green jobs. So we've got sort of a choice here. And as we automate, creating jobs, especially in the green energy industry, is incredibly valuable. And so, option one, which is the path we're currently on, is highly robotic gigafactories, where there's very few jobs at the factory itself, and there are no jobs essentially where the batteries get deployed. Every country, with a couple of notable exceptions, faces an imported mineral dependency. Okay, this is not the path to green jobs. Now, we compare that with GABES or any other geothermal heat pump based system. We've got craft, office, and labor jobs in every location. You have to make hulls locally. You cannot import hulls in shipping containers. So, and often the heat pumps themselves are made in country or certainly regionally. So this is a good path to green jobs. All right, so the summary is the biggest value for GABES is grid cost and CO2. We have to capture that if we're going to deploy at large scale. It's applicable in every climate zone. We can use existing proven technology in new ways to solve grid and building challenges. The lower cost than traditional geothermal heat pump, that helps deployment. Similar full-scale projects already exist. It creates jobs in every location. And it will be financeable. $1 billion a year is not out of the question. So that's it. I really appreciate you all joining, and I'm happy to take any questions. I want to again thank Petroleum for the opportunity to give this presentation, and we're happy to work with you on GABES or any other geothermal or technology related issue. Thanks.